So the next quantity that I want to define is the current density. Current density is this quantity J. It's a vector. The direction of this vector, the direction of the current density, is simply the direction in which the electric current is moving. The magnitude of J is defined as the current per unit area, I divided by A, as here in equation 4. Okay, so again, what we mean by A, what we mean by I, we're imagining the current flowing through, we'll imagine it being a cylindrical material, something like a electrical wire of cross-section area A. Okay, so the A that appears down here, you can think of it as being that cross-sectional area in that diagram. Okay, so the unit for the current density is, well, it's current over area, so it's amperes over square meters. And using equation 3, so there's equation 3, which has I, the current, written in terms of these other quantities. You can combine everything together and get an expression for J, the vector version of the current density J. And we find that J is equal to N times Q times V sub D. Okay, it's a vector quantity on the left-hand side, and so we need the vector form of the drift speed on the right-hand side. Okay, so there's the current density. We'll come back to that soon. I just want to point out that the model we've been using up to now to describe electric current flowing through a material is not quite right, because it is not positive charges, but rather negative charges, the negative conduction electrons that move through conductors. Okay, and furthermore, they don't move in straight lines, but rather, as you see in this picture here, they move in a much more random, along a much more random trajectory. So what causes them to move? Well, no surprise, it's an electric field. Okay, so that we have electric field lines. Here's the symbol electric field. The field lines are these gray lines with the arrows that are pointing to the left. And let's see what's happening. We have these positive charges are the positively charged atoms, meaning because they're positively charged, they're ionic. They're stripped of one or maybe two electrons, leaving a net positive charge. These atoms are fixed in place in a solid. So this lattice that in this picture over on the left, you're supposed to imagine these as being the atoms in a lattice-like structure in a solid that could represent something like copper. So these could be copper atoms that are all stuck in place. These lines that are connecting the atoms are not real lines. They're just indicating that they're fixed spacings between the atoms. Okay, now some of these electrons, as I said, are naturally stripped away from the these electrons are stripped away from the atoms. These are the conduction electrons. These are the electrons that are free to move. If we apply an electric field, well, positive charges are stuck in place. They can't move. They're immobile. But the negative charges will feel a force due to that electric field, and they will be pulled not in the direction of the electric field. Remember, electrons are negatively charged. They will be pulled opposite to the electric field. Remember, the force is Q times the electric field, and Q is negative for electrons. So the direction of the force and therefore the acceleration will be opposite. In this case, to the right, as opposed to with the electric field, which is pointing to the left. Okay, now all that says is that the electrons will accelerate in the direction against the electric field. But they don't necessarily move in that direction. What happens is they tend to move along this kind of random trajectory, and what all these sharp points in the trajectory represent are collisions of the conduction electrons with the immobile, positively charged ionic atoms. Okay, and there's a gradual movement to the right. Okay, so the electrons accelerate to the right. They accelerate ballistically, meaning They accelerate freely until they collide with one of these atoms, and then there's a transfer of energy and momentum. The trajectory changes, and then they move further. They bounce into another atom. Same thing, they bounce into another atom, but they're gradually being pulled against the electric field. Okay? And in spite of the fact that they're accelerating between collisions, on average, they move with a constant speed to the right, that is, against the electric field. Now, the significance of these collisions is when the electrons are pulled by the electric field, they collide with the atoms, they transfer momentum, they also transfer energy to these atoms, and that energy is, well, that's thermal energy. Okay, so remember when we studied thermodynamics earlier in the course, we talked about internal energy of materials, and that's all about the motion of the atoms and molecules that make up a material. These atoms in the solid are going to have energy transferred into them, so they're oscillating or vibrating around with some amplitude, with some frequency. And when you transfer energy to these atoms, well, it simply means they vibrate faster and faster, and that simply means the temperature is going to increase. Okay. So if you pull electrons through a material in this way using an electric field, because of the collisions of the electrons with these atoms, you will end up transferring energy in a thermal sense to the atoms that make up the solid. Okay? So that's why when you pass a current through a material, you will always heat it up a little bit, and you might notice a slight increase in temperature. Okay, so this is something I want you to have a good understanding of. I want you to have a good understanding of, qualitatively, of what happens when conduction electrons move through materials. Okay, let's get a little bit more quantitative about it. So we now introduce something called Ohm's law. And Ohm's law is really this equation. It's two equalities here. The first equality is, okay, J, we've introduced the current density. J is proportional to the electric field. The proportionality constant, sigma, is called the conductivity of the material. And if you think about what this means, the bigger sigma is, the bigger the conductivity, then you're going to get a greater current density, therefore a greater current, more charge flowing per unit time, for any given value of an electric field. So the bigger the conductivity, then the bigger the response to the electric field in terms of the current density. Okay, so sigma is the conductivity of a material. We define another quantity called rho. So this is not a P here. It looks like a P, but it's a Greek letter rho. And rho is simply the reciprocal of the conductivity, and we call it the resistivity. So if you know the conductivity, you know the resistivity. If you know the resistivity, you know the conductivity of the material. So a large conductivity, a large sigma, means a small resistivity rho. And it means that a large current is going to be generated by any given electric field. Conversely, small conductivity means a large resistivity. It means that for any given electric field, you'll generate a smaller current. Okay, so that's what conductivity means. That's what resistivity means. The values of these quantities, sigma or rho, the conductivity or the resistivity, these values are unique to different materials. So here are a few of them. Can't quite highlight that properly. Few materials: copper, iron, silicon, and glass. It's a small table for the resistivities of the materials. And okay, we have a bunch of different numbers here. The units are, okay, this is, the units for resistivity are ohm meters. What is an ohm? Well, that's the symbol capital omega, another Greek letter. Okay, an ohm, if I spell it out, OHM, an ohm is defined as a volt second per amp. and resistivity is measured in ohm meters. Okay, so all you need to know here is the smaller this number is, the smaller the resistivity is, the easier it is for electrons to flow through the material. So copper has a really small resistivity, and that's obviously one of the reasons why it's used for electrical wires. Iron has a somewhat larger resistivity. Silicon is not even defined to be a conductor. It's called a semiconductor. It has resistivity which is orders of magnitude, many factors of 10 larger than that for copper or iron. And then when you get to something like glass, it's many orders of magnitude larger still. A glass is classified as an insulator as opposed to a conductor. Okay, so so there's what you need to know about conductivity and resistivity. Next, we're going to introduce resistance and Ohm's law. So what are we going to do here? Let's consider a cylindrical conductor. Okay, here it is. Maybe it's a piece of, I don't know, copper or something else. And we apply a potential difference, V, between the two ends of the cylindrical conductor. Okay? If this is the high potential side and this is a low potential side, what that means, remember from an earlier chapter when we discussed the relationship between electric potential and electric field, this means that there's going to be an electric field, here it is, pointing from in the direction from high potential to low potential. So high is on the left, low is on the right, the electric field points to the right. Now, Ohm's law says that J is proportional to E, so there will be a current density J in the direction of the electric field, that is from high potential to low potential. Okay, so once again, A is the cross-sectional area, and rho now is the resistivity of this material. And L is the length from one side to the other. Okay, current density, you'll recall J was I divided by A. But we also know from Ohm's law that J is proportional to E. Proportionality constant is sigma, or equivalently, 1 divided by rho, the resistivity. Look on the previous slide. And there's also a relation that we had written down a while ago, again, when discussing the relationship between the electric field and the electric potential. The difference in the electric potential from one point to another point in the direction of a uniform electric field is simply E times L. V here means the potential difference between this side and this side of the conductor. Okay, so if you play around with this equation, solve for I, what you're going to find is that I is equal to V divided by rho L divided by A. And one way of thinking about this is that it is, you could say that V is proportional to I. And the proportionality will be this quantity here, rho L divided by A. If I just bring that to the other side of this equation, right? Then I'll get V is proportional to I. The proportionality constant we call R. R is the resistance. Whoops. No, we can't quite highlight that properly. R is the resistance. And it is, you'll see from the looking at those two equations above, rho times L divided by A. This works for a cylindrical conductor, or really any conductor that has a constant cross-sectional area A, something like a cylinder. The units of resistance are ohms, which we defined earlier.